Okay. So I'd like to welcome you all for another edition of the Quantum Fluids and Isolation seminars. So today we have Johannes Pollanen and talking. So Professor Pollanen got his Bachelor of Science from the University of North Carolina at Chapel Hill in 2002, his master's degree in 2004 from Northwestern University, his PhD in 2012 from Northwestern University under William Halperin. He was a IAQ-IM postdoc fellow from 2012 to 2015 at Caltech and Eisenstein Group. And from 2016 to present, he's been the PI of the Lab for Hybrid Quantum Systems at University of Michigan State University. And he's also been the Jerry Cohen Chair of Experimental Physics and Assistant Professor at MSU. And from 2019 to present, he's been the Associate Director at the MSU Center for Quantum Computing, Science, and Engineering. And in 2016, he was one of the co-founders of the quantum hardware company, LHQS Quantum Hardware. Today, he's going to be talking about quantum fluids and quantum information science. So please help me in welcoming, either by unmuting yourselves or by clapping virtually, Professor Johannes Pollanen.
All right. So can you hear me well?
Yeah, you sound good.
Wonderful. So thanks a lot for putting on this really wonderful seminar series and for inviting me to tell you about work that we're doing in my lab, the Laboratory for Hybrid Quantum Systems at Michigan State University. And our group, we're an experimental group, and we work kind of at the intersection between what I would call like conventional condensed matter physics and quantum information science. And you'll see how that evolves and how that brings about, I think, some interesting ideas. And the things I'm going to tell you about today are associated with how those kinds of intersections between different fields can be exciting from the perspective of bringing together the expertise of low temperature physics and that used to study quantum fluids, specifically those of superfluid helium-4 in this case, and more conventional quantum information science platforms of various kinds. So you can see here we have, helium with electrons trapped on it, or superconducting qubits, and I'll tell you about how we interface those with and integrate those with quantum fluids. But before I get to that stuff, I want to kind of give you a broad overview of some of the general things that are going on in the group, so you can kind of get a flavor for various kinds of projects, some of which I won't talk about here, but I'm happy to take questions afterwards, or you can send me an email. Yeah, so essentially all of our work, like I said, can be categorized as kind of at the intersection of condensed matter physics and quantum information science, or quantum computing. And broadly, that our projects fall into 4 categories right now. One of them involves creating these funny hybrid quantum systems and new kinds of quantum computing platforms based on electrons on helium. And I'll tell you a little bit about that kind of thing. And we do partner. This kind of effort is a partnership between Michigan State University and a private effort in this area. Joshua mentioned a company that we co-founded some time ago called LHQS to study novel platforms for quantum computing hardware. Something I won't talk at all about, but I'm happy to chat about is our work on looking at many-body quantum mechanical phases of electronic matter in low-dimensional electron systems. So these involve things like 2-dimensional electron systems in graphene, in semiconductor materials. We have some very new kinds of fun material systems based on halide perovskites that we're working on in that direction. Again, I won't say anything about that. It doesn't really fit thematically with what I'm going to tell you. And then on the quantum information, on the purely quantum information side, well, it's not purely. It does overlap, but we work with superconducting circuit-based quantum bits, and in particular, for those that know it, we use the architecture of the 3-dimensional transmon qubit right now as our main workhorse. But I'll say a little bit more about it. If you don't know what a 3D transmon is, or have never seen a superconducting qubit, don't worry, I'll say a little bit about that. And then very, very recently, we've started playing around with some fun projects associated with an altogether different kind of quantum computing platform, quantum information science platform. And those are the electronic spin states in color center defects in diamond. I also won't say anything about that work, but we just got some stuff started in that direction. So if you want to know more details about any of the things I'm going to say, read our papers, look at, you know, some pictures from the lab and stuff, you can check out our website, hybridquantumlab.com. You can also follow us on Twitter if that's something that you do, you know, stay up to date on all the things that we're up to. But so here is what I'm going to tell you about in detail now that you kind of get the lay of the land as to what kinds of expertise we have in the group. I'm going to tell you specifically about, you know, this intersection between quantum fluids, quantum computing, quantum information science. And I'll start by giving a primer to what superconducting qubits are and why they're fun. And, you know, I find this was something when we got into this game that you know, it takes time to learn and figure out how these work. And I'll try not to be pedantic too much, but if, you know, it's good to have a base to start from. And then I'll tell you about some new results that we have coupling superfluids, which is quantum fluid, in this case is helium-4, to superconducting quantum circuits. And so we've been working on two various kinds of things here, coupling these quantum fluids both to superconducting transmon qubit systems and also to other quantum circuits, namely single electron transistor devices. And it turns out that in this situation, what we found is that the quantum fluids are really a fantastic tool for investigating qubit coherence and learning something about that in these superconducting circuits. Now, this combination of superconducting, the tools of superconducting circuit quantum electrodynamics and superfluids also paves the way for some pretty new ideas for developing altogether new and exciting qubit platforms based on trapped electrons. So I'll say a little bit about our efforts in that direction and what we're after. But the goal essentially is to develop new kinds of qubit platforms with different levels of connectivity and coherence and exciting possibilities that you can't get in other quantum computing platforms. And then time permitting, and I'll be very careful to not abuse your time. I'll tell you about some very new results we have on developing some initial steps toward flying electron qubits using coupling to piezoacoustic surface acoustic waves in piezoelectric crystals. So that's what I hope to tell you about. Okay, so intro qubits, superconducting qubits 101. So you want to make a circuit and you want it to be a qubit. So how do you do it? Well, quantum states are super fragile, and so you'd like these to be made from dissipationless materials. So let's make them out of superconductors. We can just make a circuit. It can have an inductor and a capacitor, and you know, this LC oscillator is a great, you know, circuit, and we can turn it into a quantum LC oscillator. Here's the energy of the classical LC oscillator, but what we can do is we can write a Hamiltonian that describes the electromagnetic excitations in this kind of circuit, and we can quantize it, and we get a quantum harmonic oscillator, and with well-defined energy states, in principle, that you can, you know, excite a transition from here to here. But there's a big problem here because you've made a nice superconducting circuit, but each one of these energy levels, because this is a completely harmonic system, is equally spaced. So you have no way of individually addressing any one of these levels without also simultaneously, you know, kicking excitations around on the entire manifold. And so that's not a terribly great. Schrodinger's cat does not get happy about making quantum computers out of harmonic oscillators. But there's a nice way to avoid this, and that is that you introduce some amount of nonlinearity, some amount of anharmonicity, by having a nonlinear circuit element known as a Josephson junction. And this is this little X on a wire here is the diagram that you use to represent one of these Josephson junctions, but it's a pretty simple device. It has a superconductor on one side, a superconductor on the other side, and separated by a thin insulating barrier. So in our cases, the superconductors are aluminum on either side, and the insulating barrier is aluminum oxide. And then the quantum degrees of freedom in this simple picture are that you get Cooper pairs that can tunnel coherently across this insulating barrier, and they actually form in this kind of device the quantum degree of freedom that really enables quantum computing. So what has happened? So like I said, this this Josephson junction takes the linear inductor that I had in the previous case and makes it a nonlinear inductor that depends on the current, the tunneling current that's flowing through the superconductor. And if I want to make a circuit out of that, I just replace my linear inductor with this Josephson junction, and there's some parameters that describe the capacitance. This looks like a capacitor. There's two metals separated by a little insulating barrier. We're going to keep the real capacitor, the real classical capacitor over here, and then there's this Josephson inductance. But this forms a nonlinear LC oscillator, which we can also quantize this circuit, and we get a Hamiltonian that looks like this. It has a term that's associated with the charge degree of freedom, and a term that's associated with this Josephson energy, so the tunneling of the charges across this insulating barrier. Now, this charging term, I'll note, has this little offset and little n sub g, and I'll come back to that in just a moment, but just keep that in mind. But it turns out this thing works wonderfully as a qubit. And in fact, by tuning CJ, LJ, and CG, what we can do is we can get the qubit transition frequencies to be in the range of 4 to 8 gigahertz. And what I'm showing you here are just a bunch of these different qubit transitions. So this is the ground state of the qubit. This is the first excited state, second excited state, third excited state, etc. Now remember, I mentioned there's this little offset charge, n sub g. And that's because if you bring some outside charge, or there's some environmental fluctuations in the charge environment of this thing, it will shift the qubit frequency around. So you have this beautiful anharmonicity, but if this n sub g, which sometimes you have control over and sometimes you don't, is fluctuating around, then your qubit transition frequency is going to fluctuate, and that's not going to be so great. But more on that in just a moment. So this 4 to 8 gigahertz range is fantastic because it's compatible with a lot of microwave, commercial microwave equipment that exists. But it's also nice from the perspective that if you convert this frequency into temperature units, you get something that's around 250 to 500 microkelvin. And our dilution, so if you take this kind of circuit here, it's a relatively simple circuit, and you put it in a dilution refrigerator and you cool it down to 10 millikelvin, you're going to with high probability initialize the ground state of the qubit. So that's great. Now, but we have to solve this issue of n sub g. Thankfully, we don't have to solve it. This has been solved by the development of the community over, since about 2007, and probably even earlier than that. And that is that if you tune the parameters, this CJ, LJ, and CG, and change them in the geometry and the fabrications in just the right way, that you can change the ratio of the Josephson energy to the charging energy and make it relatively big. So let's not make it 1, as is the case over here on the left-hand side, but let's make it 50. And then what you see is you lose the anharmonicity between the levels. You lose some of it, but you gain in the flatness of these levels. So now this, as a function of this offset charge, so now fluctuations in this Ng are no longer deleterious to the qubit properties of the qubit. And this was this regime over here is often referred to as the transmon regime, and the qubits that have this kind of property are referred to as one kind or another of a transmon. Just to give you some idea, it wasn't just this advance, but advances like this in trying to understand the device properties of these kinds of circuits are really what have allowed superconducting qubits to go from, like, the late 90s of having coherence times and energy relaxation times that are like on the nanosecond time scale to what we have today, which is like hundreds of microseconds that routinely that can be achieved in these kinds of qubit systems. We can't get quite that high, but we can get many tens of microseconds in our group. But that being said, you think, okay, hundreds of microseconds, that's pretty awesome. But why isn't it hundreds of milliseconds? What can we get it higher? And questions about trying to get this number to be just a little bit higher even are important from the perspective of quantum error correction. So you can, if you can push this up to, the millisecond or tens of millisecond level reliably, then I think it opens up, you get, at least by some estimations, close to the thresholds needed for large-scale error correction, which would be really the next level of quantum information science in some sense. But what I'm going to tell you a little bit about is how do we go from here to larger values. So, oh, before I do that, I've just shown you cartoons. This is what actual, oh, somebody's got a question, I think.
Can I just ask a very quick question?
Shoot.
On the previous slide, you said you really cool it down so that you can use the bottom levels as a qubit.
Yeah.
How do you generate multiple qubits this way?
So this is all just for a single qubit. So then you would have multiple of these circuits, each fabricated individually. And I can show you it on the next slide. And then those would form an array of qubits that you could couple. And I'll say a little bit more about how they're coupled. Is that get at your question?
Yeah, no, because I was concerned maybe you're going to use the higher energy levels for as different qubits, but
no, I mean, in principle, people have ideas about how to use these multi-level systems, and there are these other levels, and so these are often referred to as qubits, and there are great ideas there. I won't be saying that's not what we're doing. We actually do use the other levels for diagnostic purposes of various kinds, but yeah, everything here I'm going to talk about is usually one qubit or one qubit where we're only worried about these lower two levels.
Yeah, great, thanks.
Yeah. And so here's what the state of the art kind of looks like if you go on Google and type in what do superconducting qubits look like. These are chips from IBM. Here's a transmon chip from Google, which I think they now refer to as the XMON, or the GMON. I don't know. They change the name of the things all the time. And here's a chip from Rigetti. And so you can see when I said, you adjust these parameters, change the fab, these architectures are quite a bit different from one another, but they all have this key element of Josephson junctions and capacitances, essentially, that allow you to create these kinds of qubit levels. Now, there's some other features here that you see, these wiggly lines, and I'll say something about those because I haven't said anything about how you actually connect, measure, or control one of these qubits. And so I'll show you the variant of the transmon that we use in our group. It's a little bit different. So the way in which you actually couple to all of these superconducting qubits is via a microwave resonator that is coupled to the qubit. In our case, we use what's called a three-dimensional transmon, and it's three-dimensional because actually the qubit lives on this little chip in the center, and the way we do the control and readout is via this large-scale macroscopic three-dimensional microwave resonator. So if I were to zoom in on this little chip right here, you can actually see at the heart the qubit itself. So here are two Josephson junctions this is actually a qubit that has two Josephson junctions, distinct from the one that I showed you previously, but you can have their technical details for wanting multiple Josephson junctions. And then it has these wires that extend off out of the view here. And if you look at this panel on the bottom left here, what those wires extend to are large scale millimeter sized antenna pads. And those antenna pads talk to the microwave modes of this three-dimensional box. And so then if we shine microwaves in and measure what comes out, we can both address the qubit, we can prepare any superposition state on the Bloch sphere, we can do full tomographic readout of that state, we can do measurements of T1, the energy relaxation, T2, the dephasing, all of this stuff. And yeah, so this thing's called the 3D transmon. That's what we do. In this previous slide that I showed you, those little meandering lines on the chip that IBM and Google and company use are microwave resonators also, but they're just patterned onto the chip. Okay, so I said already that we use these microwave fields to do the measurement, but I want to say a little bit more because essentially what we're doing is we're just borrowing from quantum optics. We're using techniques associated with this term, circuit quantum electrodynamics, and what that really just means is you put a two-level system inside of a high quality factor photonic resonator. Here the photons are microwaves, and then the physics is governed by the Jaynes-Cummings Hamiltonian from quantum optics. So this Hamiltonian essentially encapsulates much of the physics that we're interested in. So it has a term associated with the qubit, that's the sigma z term and omega q. It has a harmonic oscillator term that's associated with the microwave cavity, that's its omega c. So these are just photon annihilation and creation operators in the microwave field of the cavity. And then it has a term that couples the qubit and the microwave field with some coupling parameter G. And I'll say a little bit more about G in a minute. But essentially what this allows us to do is to input a microwave photon, take the qubit from the ground state to the excited state, or extract a photon and the qubit, goes from the excited state to the ground state. And we can tune the resonances of these cavities to be, in close to or in the vicinity of the qubit frequency. And so that's it. We just measure the microwave field and we control the qubit with the microwave field. We measure the microwave field to figure out what the qubit is doing. And this is kind of what some of the beautiful data looks like when you do this. So this is a Ramsey fringe experiment that we did on one of our qubits. And this is just to give you some idea of what, I said hundreds of microseconds are typical for superconducting qubits. We're not quite that good, but we get into the tens of microseconds with our latest devices. And the other thing I want to highlight here is that this is really a fantastic collaboration that we have with my colleague Kader Murch at Washington University in St. Louis. So it's a real we've had a lot of fun getting this kind of stuff started, and we're going to keep it going for a little while. So now we get to the meat of it. I'll tell you a little bit about what quantum fluids bring to the table. I'll mention also here my colleague Kader Murch is not only a fantastic physicist, but he's also he's a talented artist as well. So whenever he writes a paper, he always makes some little cute cartoon of that kind of encapsulates the physics of that paper. And this is the one that he made for the one about the results I'm going to tell you today. So we started this project essentially saying, like, what can we learn if we put a superconducting qubit inside of superfluid helium? And this was partly motivated from previous experience that I'd had studying two-dimensional electron systems in gallium arsenide, where the 2D electrons in the gallium arsenide semiconductor material can be at elevated temperature relative to the cryostat in which they're being measured. And so in what we would often do is we would take our samples and we would put them inside of superfluid helium and to try to cool them down better. In that case, it was helium-3, but it would allow the electronic degrees of freedom to cool more readily inside of this helium immersion cell. And so we said, can we do the same thing with superconducting qubits? So there were a bunch of questions that one can ask. We're essentially changing the circuit quantum electrodynamic vacuum by introducing helium. What kinds of effects does that have on the qubit? Can we improve the thermalization and possibly the decoherence in these superconducting qubits by doing this kind of thing? That's what motivated us largely. And then we were also motivated by some work that our colleagues, I think John Davis is in the audience actually right now, his group did some beautiful work a few years ago now, where they were looking at using superfluid helium as a way of tuning microwave resonators. And so they can, fill very systematically these three-dimensional microwave cavities and watch their frequencies change. And this has actually led them to other kinds of experiments where they've really gotten some amazingly large amounts of tuning using quantum fluids. And this is partly one of the aspects of helium that makes these kinds of experiments exciting, is the fact that it is such a low loss microwave medium. It's very, very conducive to these kinds of high coherence and high fidelity, high Q quality factor measurements. So anyway, that's what we did. We said, let's go a step further and actually do a qubit experiment like this. So we built a three-dimensional microwave cavity into which we could pour superfluid helium-4 and then do all of the measurements. So let me tell you what we found. So remember I mentioned that we essentially are working in a tunable vacuum. We're changing the dielectric constant of the vacuum surrounding the qubit. And what we see is, what I'm showing you here are the response of the cavity to the introduction of superfluid helium. So this is very similar to what Professor Davis's group saw. We can see a shift in the cavity resonances as we fill the cavity with superfluid helium. So there we're really just filling a classical capacitor with a new dielectric, right? That's what's leading to this shift. But we can also measure the properties of the superconducting qubit, and they shift as well. So the blue traces are all when there's no helium, and the red traces are when we add helium. So we see a systematic shift of the qubit transition. This is the 0 to 1 transition of the qubit, and these transitions over here are the 2-photon 0 to 2 transitions of the qubit, and they both switch. And so we said, okay, we should be able to understand these properties from within the context of circuit quantum electrodynamics and the Jaynes-Cummings Hamiltonian. So what we do is we take the spectroscopic data that we can measure, both with and without helium present in the experiment, and we use that data as inputs to fit a generalized Jaynes-Cummings Hamiltonian to extract the Josephson energies, the charging energies, and these couplings between the qubit and the cavity, both in the cases where the experiment has helium and without. And so we find that, the Josephson energy, unsurprisingly, doesn't change so much depending on whether you have helium in there or not. It's really just related to the critical current of the junction. The capacitive charging energy does change by about a little less than 1%. And we can understand that from just how the electric field lines redistribute themselves when we introduce the helium into the thing, and we can do finite element modeling that matches this kind of thing. But then the coupling of the cavity and the qubit is a little bit more tricky, because the qubit and the cavity, when you go to low temperatures and low microwave powers, because of this coupling term in the Jaynes-Cummings Hamiltonian, the qubit and the cavity are no longer really each individual objects. They hybridize, and there's strong interaction between the two. And so actually figuring out all the details of why the vacuum Rabi splitting, or the vacuum Rabi coupling of the qubit changes by this amount requires us to think about two things. And what it requires us to think about is the fact that I mentioned the electric field line distribution within the cavity changes. But remember, we're also changing the vacuum of circuit quantum electrodynamics. So you have to take into account the fact that the 0-point fluctuations of the microwave field are modified, and then those modifications lead to shifts in the qubit frequency. And you have to take both of these into account. And if you do so, you find that the total shift is about around 3%, very close to what we measure in the experiment. But yeah, so two things change. We change the vacuum, and we change where the electric field lines are subtly. And you have to understand both of those. Okay, so that's great. But what about the qubit coherence? Did we do anything to improve or maybe make the qubits worse? And so what I'm showing you here is data of the energy relaxation of the qubit, or T1, as a function of temperature, both again with and without helium. And what we find is that at the lowest temperatures, T1 doesn't seem to care at all whether we have helium in there or not. Well, that's both good and bad. It's good in the sense that, dumping a whole bunch of helium around the qubit doesn't actually completely screw it up in some way. But it's important to, it's also consistent with the fact that cooling helium, superfluid helium-4, down to temperatures below 50 millikelvin is actually quite an effort. There's a large Kapitsa boundary resistance, which is well known in the low temperature physics community, that prevents heat from getting into or out of helium at very, very low temperatures. So this is not so surprising. But what we find is that at intermediate temperatures, we see this systematic drop in T1 when we have superfluid in the system. So that's okay, because we never operate the qubit out here at 100 millikelvin. We operate it down here, so this doesn't affect the performance. But we wanted to know what on earth is going on for this reduction in T1. And what we've hypothesized, based on some work that was done on looking at superconducting qubits that are coupled via phonons in a substrate, is that maybe what's happening is, as we heat up the helium, maybe there's going to be more thermal excitations, phononic thermal excitations in the helium, and maybe those are mediating by one way or another energy transfer to the qubit and leading to a larger quasi-particle density in the aluminum. So these would be unpaired Cooper pairs in the superconducting qubit. This is a hypothesis. And we said, well, if that were the case, that would, if this shift in T1 downward, if we assume that it's entirely produced by additional quasi-particles, how many would we need? Well, the change in quasi-particle density would be around 4 times 10 to the minus 6, which is not inconsistent with what people have seen in other kinds of experiments with athermal quasi-particles in these systems. But then again, if this is true, then that should lead to a shift in the qubit frequency that you can calculate. around 14 kilohertz, and we can measure the frequency shift as a function of temperature. And actually, we do see a shift downward, a systematic shift downward that's consistent with this. So we think that this effect is somehow associated with the excess quasiparticles in our qubit, and that the helium may in fact be playing the role here. And we actually, so again, this is a hypothesis, not smoking gun evidence for this hypothesis that I'm telling you, but we do have new experiments underway that will hopefully sort out whether or not this idea is right. And I can say more about those if you have questions. But how about dephasing? So the qubit can also not just lose its energy and go from 0 to 1, but it can lose if you create a superposition state, it can lose phase information of that superposition. And so what I'm showing you here is the dephasing, this is T2, the dephasing time of the qubit as a function of temperature. So what we find is that as we cool down, the pure dephasing of the qubit actually improves. We get better T2. And so that is kind of surprising and good. Adding helium makes the qubits more coherent. And we said, okay, well, what could be causing that? Well, it's known via other experiments that there are hotspots within the experiment itself, both in the microwave environment that the qubit is coupled to, in the substrate, all kinds of things. And so we said, okay, well, maybe the microwave environment that the qubit is seeing is actually warm. So what if we assume that to be the case? And actually, for the kind of qubit that we're studying here, which is a single junction transmon, it's been seen in a number of measurements that these kinds of hot photon effects are in fact what limit the dephasing in these qubits. And we can calculate how much, if we assume that there are just some residual photons at a higher temperature than the base temperature of the cryostat, how much dephasing do we need to get? And so for our data here, for the pure dephasing, we have to increase the temperature of the photonic, the microwave environment only by about 10 millikelvin to understand the differences between when we have helium in the system and when we don't. And that kind of very minor temperature difference is not terribly surprising for helium-4 in this kind of temperature range, and seems very plausible to us as an explanation for why we're seeing improved dephasing. And you might say, well, what about the qubit itself? Maybe it's a little hotter and there's some weird dephasing thing there. And we can sort of suss that out also by measuring the residual excited state population of the qubit as a function of temperature. So this is what the data here is if we do absolutely nothing to the qubit, it should go to its ground state 100% of the time at t equals 0. But we're not at t equals 0. All of our data clearly indicate that. We're not even nothing seems to be at the base temperature, not at the 10 millikelvin of the base temperature of the cryostat. So if you're not at t equals 0, what this is a measure of is how often does the qubit just accidentally get kicked up into the excited state. And what we find is that first of all, follows a really nice Maxwell-Boltzmann calculation. So this is a great proxy for, in some sense, the qubit temperature itself. And what we find is that the residual excited state population bottoms out at about 1%, regardless of whether or not we have helium in the microwave cavity. And so that really tells us that, we're not the helium. And I'll notice again that this is the residual excited state population is again flattening out below around 60 millikelvin. It's starting to plateau. So we're losing good thermal coupling to the helium at those temperatures. So it paints a nice picture that's consistent between all of these different measurements. So yeah, we don't think we're actively cooling the qubit. We think we are cooling the microwave environment though, using helium. And if you want to know, there's devil in the details that I've swept under the rug here, associated with, some of you may be wondering about two-level fluctuators and various other kinds of decohering and energy relaxation phenomena. And we discuss those in gory detail in this manuscript. So if you want to have a look at that, it's there, or you can ask me, and I can try to remember. Okay, so that's the story. So we do see that these superfluids can tell us something about the decoherence properties of qubits. Let's now apply them to another kind of quantum circuit, a single electron transistor. So these single electron transistor devices have some elements in common with superconducting qubits. They have Josephson junctions here that separate, say, a source lead from a superconducting SET island. So SET stands for single electron transistor. And then there's another Josephson junction here that connects to a drain. So this looks very much like a transistor. There's a source, a drain, and then off on the chip somewhere else is a gate that allows us to control the current through this device. So the thing you should take away is that these single electron transistors, they're called single electron because they are extremely sensitive charge sensors. So the charge sensitivities of these devices can be at the micro electron per root hertz level. So they can change, and the way in which that sensitivity comes about is that the transport through this device is tunneling transport of single electronic excitations, quasi-particles, as shown here, Josephson quasi-particle tunneling, double Josephson quasi-particle tunneling. There's a whole zoo of different kinds of tunneling processes that dictate the transport of electricity at low temperatures through this kind of device. And so this is a color map of the current through one of these SET devices as a function of the source drain bias here on the vertical axis, and this gate voltage, which you can't see on the image. And so we see all these great tunneling features that you would expect to see. And the question is can these quantum fluids help us to investigate the performance of these SET devices? And the answer is yes. But when I say performance, what I mean is something like this. So here I'm showing you differential conductance through this kind of device. Again, source drain bias on the vertical axis, gate bias on the horizontal axis, and you see all this kind of salt and pepper noise throughout the Coulomb diamonds that form up here. And these are produced by two-level fluctuators that are coupled to the SET in some fashion. So they could be on the substrate, they could be in the oxide barriers of the Josephson junctions, and they produce this kind of flickering noise in the transport through one of these SETs. And in fact, so when I say two-level fluctuator, what you should have in mind is this kind of energy landscape that's in this inset right here. We have just a double well potential with some kind of electrostatic object within the substrate that can reconfigure its energy between these two minima. And now I'm saying nothing about really what the mechanism is here that creates this picture, because honestly, there's a whole different slew of things it could be. In most cases, we have no idea what it is. But these two-level fluctuators do have a very specific expectation for their noise power as a function of frequency, and it should be this telegraph noise spectrum. And so what we can do is we can measure the noise spectral density of one of these SET devices, and we can actually identify these via this telegraph noise various kinds of two-level fluctuators that are strongly or weakly coupled to the single electron transistor. And that's great. But what about the quantum fluids? So what we're going to do is we're going to take one of these SETs and we're going to submerge it systematically in helium. And what we find, what I'm showing you here is data of the ratio of the dwell times of the two-level fluctuator, whether it's in the left minimum or the right minimum. We can extract this from essentially the time traces of our noise spectra. Oh, sorry, of our noisy transport. And what we can do is we can plot the ratio of the amount of time that the fluctuator remains in the right minimum versus the left minimum. And it should follow, this ratio should follow this kind of activated temperature behavior. And we can actually extract now from these kinds of, we can get a sense of the relative changes in temperature of the defects themselves from these kinds of data. And what we find is that if you're at low temperatures or high temperatures with the SET in vacuum, you really, you don't see any real difference. You see a little bit of degradation in the dwell time at high temperature. And if you are at very low temperature, say 7 millikelvin on the cryostat, and you have liquid helium around the SET or not, you really see no change in this dwell time. So the defects aren't doing anything. So our conclusion from this is that the lowest temperatures, helium doesn't affect the TLS temperature. And the reason for this is that the same reason that T1 didn't change in the superconducting qubit case. We have a large Kapitsa boundary resistance that's keeping things from the helium doesn't have any excitations at these kinds of temperatures to really help you. But if we raise the temperature, we do see a marked difference in the, so what we're gonna do is we're gonna raise the cryostat temperature and add helium. And what we find is that these elevated temperatures, the dwell time between the ratio of these dwell times dramatically changes and indicates that actually what the helium is doing is helping to cool the two-level fluctuator by about a factor of 3, we estimate, in this kind of situation. And so this is nice because it kind of gives credence to some of the ideas that we had in the superconducting qubit case that about what the quantum fluid was actually doing to the qubits, and paints a kind of nicely consistent story. Okay, so the last two sections I will go through pretty quickly, but it will build, the next step will build on these single electron transistors. So we've learned something about the coherence properties and the noise properties of these kinds of devices, but really one of the things that especially the single electron transistor work does is it allows, it's part of our effort to springboard and develop a brand new kind of fantastic brand new fantastic qubit based on electrons that we trap on the surface of helium. So I'll tell you about that next. So for those of you that don't know, this is the crash course in electrons on helium. You have helium, it forms the substrate, and we're gonna place individual electrons onto the surface of the liquid helium, and they're gonna float about 10 nanometers above the helium surface. So the reason they float like this, let me mention, I have little kids, so I apologize for it's nap time. And our oldest one was sad that he couldn't come listen to the talk. I told him he could watch it on YouTube later. So these electrons, they float on the surface of helium because of two competing effects. So they're charged, the helium is dielectric, and so the helium forms a positive image. You get a positive image charge that forms in the helium, and the electron wants to attract itself to that helium, that image charge, but it can't get into the helium because of Pauli exclusion. And so this balances out, and the electrons just float on the surface of helium. And this is an amazing because it's extremely clean. It has the highest 2D electron mobility of any system in condensed matter. And unlike semiconductor two-dimensional electron systems, it forms a non-degenerate 2D system. And because this helium doesn't provide any screening at all, the Coulomb action is really strong between these electrons. They really see each other. And because of that, it forms two kinds of phases of matter. It forms a strongly correlated electron fluid at high temperature, and then at low temperature, it actually crystallizes and makes a regular triangular lattice surface of helium. Now, because of this extreme cleanliness, the electron internal quantum degrees of freedom, its spin and its motion relative to the helium, have been predicted to be long-lived qubits that people have been talking about for some time, but are really only getting the technological capabilities to explore recently. And these are the degrees of freedom that I want to talk to you about from the perspective of qubits. So here's there's essentially three kinds of qubits that I want to tell you about the electrons could be. So the electron, like I said, is trapped on the surface of the helium, and it's a ladder of Rydberg-like levels normal to the helium surface. So the electron can actually up and down. Its wave function can change its relative position normal to the surface. And this forms a Rydberg ladder of energies that are spaced by, the lowest energy levels are spaced by around 120 gigahertz. And this is the original proposal for doing quantum computation with electrons on helium by my colleague Hickman here at Michigan State University. And there's a number of groups around the world working on this, and we're thinking a little bit too. Now, the other thing that it has is its spin. So the spin itself could be a qubit state, and it's been predicted that it should have very long-lived coherence on the order of seconds. Much like, you know, spins are in semiconductors are really fantastically high coherence, you can get similar kinds of things here. And my colleague Lion at Princeton is actively working on this, and also Erika Kawakami, who just started a lab at RID Japan. Now, the qubit that we're at the moment trying to develop is one where we don't worry about the confinement of the electron to the surface, but we provide lateral confinement and engineer a trap for a single electron. And then the motion of the electron in this trap forms the quantized motion will form the qubit states, and engineer these traps so that they have frequencies, motional frequencies of around 5 gigahertz. I'll make Schuster. It's actually an idea that was turned on to by my colleague Dave Schuster at the University of Chicago, and he's working on this actively also. So at the heart of our approach is first the trapping of the electrons. So we do this in these microchannel devices where we carve out a little, you know, this is maybe 5 or 6 microns wide, a micron or 2 deep, maybe 500 nanometers deep, and we can get electrons trapped in highly controlled inside microchannels. That's a cartoon, but this is what the actual devices look like when we fabricate them, and this is the transport of electrical. We can characterize these microchannels. We have just rows of electrons in this microchannel region that we can slosh back and forth and measure the transport. So we can both control how many electrons we have in there and also how strongly they're confined laterally. So that's the side gate potential allows us to confine the electron rows, and this back gate potential eventually allows us to control the density. And what we see is we can have there are no electrons in the microchannel and we see no current. There's a region of high conductivity microchannel, and that's an electronic fluid that flows in the channel. And then if we go to higher confinement, we can actually crystallize those rows of electrons. So this is a Wigner crystal in quasi 1D confinement, essentially. And I want to draw your attention to these little features just to give you a sense of how well we can control this system. Each one of these little fringes corresponds to an additional row of electrons being added to the microchannel. So right here, you know, there's a row of 500 electrons, a single linear row of 500 electrons, and then we add 500 more and create 2 rows of with 1,000 electrons total. Then to make a qubit, what we do is we create a little extension off of the side of the microchannel and produce a single electron trap that has an RF, a fast single electron transistor in it for these qubit states. That's what we're building up. Just to give you a little bit more sense of what the actual designs look like, they look something like this. None of this is important really for the purposes of this, except that at its heart, we have these single electron transistor devices. And what we can do is we can do finite element modeling in electrostatic environment and then solve Schrodinger's equation self-consistently in that potential to get the energy levels, their anharmonicity, and we can actually even see what the spatial distribution of the electron waveforms is like, or what we would expect to see in our experiments. And so we're still in the design and build-up phase of we're actually combining a lot of these pieces that we know independently, the SETs, the microwave control, the microchannels in devices. And our readout scheme, like I said, uses one of these really fast SETs. So that's where the SET back in. And yeah, there's details here, but they're not for these purposes. Okay, I can really finish this last part very fast about coupling very new results we have in piezoacoustics to electrons on helium, and the prospect that maybe one day one might imagine a flying qubit with this. So what we do is we are going to use piezoelectric surface acoustic wave, or a SAW, to transport electrons. So what is a surface acoustic wave? Well, if you have a piezoelectric substrate and you pattern an interdigitated transducer onto that substrate and apply a high frequency signal to that interdigitation, it launches an elastic wave via piezoelectric coupling along the surface of this crystal. That elastic wave, also because of piezoelectricity, has a co-propagating electric field. And so what that does to nearby charges is that electrodynamic SAW potential will hold of these electrons and drag them along with it. And so one can create piezoelectric transport or high frequency charge pumping with this kind of technique. And people have done this kind of thing in semiconductors for a long time. That's actually, I learned how to do these kinds of things when I was a postdoc at Caltech studying bilayer and single layer quantum pulse. But coupling surface acoustic waves to 2D electrons is exciting, both from the perspective of physics. There's a whole host of cool experiments one can imagine doing that have been done in semiconductors that could do analogs of these experiments in the electron on helium case, which is unique because of its properties. Or you can try to do some quantum computing kinds of things. So for example, you could imagine trying to do metrologic high frequency charge pumping with electrons on helium, or create ways of taking an electronic state that you've prepared over here and a spin state and transport it along the helium. So these ideas have been around in the semiconductor community for a long time. One of the big problems, excuse me, doing these kinds of experiments in semiconductors is that the coherences of a flying, and by flying I really mean that you spatially take this thing and you drag it to some other location, is that these semiconductor materials have, charge dopants, they have nuclear spins, they have strain fields, all kinds of spin-orbit interactions as the electron propagates, they're decohering. None of those problems exist with electrons on helium, on the surface of helium. No, none of that. There are probably other problems, but at least it doesn't have those. And so we thought, let's try to do these kinds of measurements with electrons on helium. They haven't ever been done, so we wanted to see if we could do it. So what we did is we built a device that has an electric substrate, surface acoustic wave launchers. We can cover the whole thing in a very, very thin film of qubit, put down electrons, and then we have these electrodes underneath the substrate that allow us to detect whether or not we're pumping charges with the surface acoustic wave. So what I'm showing you here is just the surface acoustic wave device itself. So we see a resonance where we designed this device, an acoustic resonance. And then what we can do is we can measure the acoustoelectric current as a function. So we see that there's a peak that coincides exactly with where we see the SAW resonance. And so what this shows is that we're really showing acoustoelectric charge pumping in this system. And we can do a number of controls to tell us that this is really coming from the electron on helium the system. Some of those controls involve the fact that the acoustoelectric current is linear in the power that you apply, and it more or less is. And it turns out that we can take acoustoelectric current, which is what the color scales are here, and we can actually gate tune it. So you can actually control it on and off by applying appropriate gate voltages to some of these underlying electrodes. So this is, if you ever want to make a flying qubit with electrons on helium, you have to do this first. That's what we've done. So this is we're following the route of the semiconductor approach in this case. But these do really open a door for an entirely new class of experiments that one can imagine doing with electrons on helium outside of even the quantum computing stuff that I'm saying. But that's pretty much it. That's the whole story. So I hope I've convinced you that superfluids, quantum fluids are compatible with the ideas of quantum information science. There's fruitful cross-pollination between these fields. And finally, I just want to thank the folks who actually do all of the heavy lifting. This is a super dated picture, and my group members are probably laughing at me right now. But all of the folks on here, in one form or another, have contributed to a lot of the work that I'm showing now. Justin Lane, Heejin Bian, Liangji Zhang, and Camille Michaelis are the graduate students who are currently working in the lab. But a whole bunch of Basin Gulov is a postdoc who is world leading expert in electrons on helium. And yeah, none of this would be possible without them. And finally, I want to thank my collaborators both at MSU, Kader Murch again for all of his help on the student qubit work. We do have a private effort with collaborators in the private sector, namely David Rees, Nick Farina, Dave Ferguson, and Faye Waddleton, who are helping us to try to stay at the next level and really outspin this stuff outside of the lab and develop a whole new platform for computing. And of course, there are the people who pay the bills. None of this would be possible without support from a variety of different funding sources. And I'll mention, if there are postdocs and grad students who are thinking about what they want next, we do have a new multidisciplinary center at Michigan State University, MSUQ. It's the Center for Quantum Computing Science and Engineering. It involves a whole host of departments, a bunch of people working on all kinds of different aspects of quantum information science. And so, you know, if you're interested in what you might want to do for grads or looking for a postdoc, you know, let me know and we can chat. Oh, and I wanted to thank my partner in crime, my theory colleague, Mark Dickman, who really it'd be impossible without his knowledge to do any of this. And that's it. I'll take any questions that you have. Sorry for going so long.
Okay, so if you have any questions, you can just unmute yourselves or raise your hand. So John Davis.
Shoot.
Hey, Johannes, nice talk. Thanks for that.
Thanks.
Just one quick question. When you were talking about the helium in the electrons on the helium in the channels,
Yes.
I didn't get the size scale of the channels. Like, in particular, like, are there
Yeah.
constraints on the depth and the width?
Yeah. So at some point, so our microns are about, in length, they're about 100 microns. In width, they're 5 microns, give or take. And in depth, we're trying to hit something between 500 nanometers and a micron. So they're shallow, micron scale.
What
depth,
sets that depth? That in particular, that depth. What sets that? Why do you
just the
want it to be
fab.
500 or a micron?
Yeah, some of this is we need to get this. So for the qubit readout via we need to tune the sensitivity, and so knowing exactly if we move it too far away, we won't have the sensitivity to read out. So I didn't explicitly say this, but I should have. What we're detecting to determine whether we have the motional state of the qubit is actually the redistribution of the electric field when the electron changes its spatial charge configuration. And so we need to be sensitive, not just presence of the electron, but in its shape when it goes between the ground state and the first excited state.
And so you're actually, it's like hovering above a set.
That's right.
Right. And you want it to be close enough to the set that you get good resolution.
That's right.
I see. Got it. Cool. Thanks.
There are other ways to do this, but that's what we're currently
No, that's good. I just wasn't clear on that.
Yeah.
Cool. Thanks.
Any other questions?
I would like to ask a question. Perhaps you already said this, but on the electrons floating on the liquid helium, because they have also all interactions, the long-range Coulomb interactions, is there a possibility to check if they form a Fermi liquid or not? Do they have plasmonic modes?
Yeah, so there are plasmonic modes, but they're much more classic ones. And so the densities in this system, that's one of the things that I mentioned it at one point, that the system is quantum non-degenerate. So if you could get the density much higher, you could reach the Fermi liquid regime. So for the densities that we currently have, though, which is 10 to the 9, if you calculate what the Fermi temperature will be, it's like a millikelvin. So, and to really, so this is in contrast to gallium arsenide, where you have 11 per centimeter squared. Here we have 10 to the 9 or 10 to the 8. And so the system, the electrons don't have strong wave function overlap with one another. The extent of the electron function is like hundreds of nanometers, and the spacing between them at that density is like micron scale. So they're really isolated individual electrons. Does that get at the heart of your question?
Yeah, thanks.
This is the idea, but getting the density up is actually technically challenging.
I see.
It would be if you could do it, it'd be fantastic though. It'd be a very cool experiment.
Right, thanks.
So any other questions? So in relation to the last question, I mean, instead of increasing the density, is any way to like increase the interaction strength? So then they would form, say, like some kind of, because I mean, you can model like a unitary Fermi gas with a Fermi liquid like model, right?
Right. So these two things are actually strongly related to one another, right?
Yeah.
So right now, if you take the electrons and you go to if we take a very thick layer of helium and we put the electron, they'll naturally get it. You can get a density that's like 10 to the 9. You can essentially put more electrons down, really, pull them in with electrodes to really try to increase the density. But when you get a lot like 10 to the 9, the electrons actually start diving under the helium surface. And it's because the interaction between them is so strong. They actually they freak each other out and they don't want to be next to each other. So what you have to do to get the density up is to actually you have to introduce some amount of screening so that this bare Coulomb repulsion can't just destroy the system. And so what you do is you make a very, very thin layer of helium above a metal load. And then what you can get is you can get the electrons to pack in a lot closer and get the wave functions to overlap. It's a little counterintuitive, but what's actually happening is you're softening the Coulomb interaction by having this metal screening layer under, and weakening the interactions. I mean, you'll have different kinds of interactions, right? Because exchange will be important, and that'll be exciting for a whole host of reasons. You don't want the long-range Coulomb. You have the really strong repulsive Coulomb interaction.
Okay. Any other questions? So maybe I'll wait 5 seconds if anyone wants to unmute themselves and ask a question. Okay, let's thank Professor Pollanen again.
Yeah, I appreciate it. This has been super fun. Thank you again for inviting me. Yeah, if anybody does have other questions, feel free to email me. Yeah.